Hi, everyone. Thank you very much for joining us today. We will now introduce Don Donofrio, instructor consultant at the Snell Group. He'll be giving an insight on mechanical infrared inspections today.
Hello, and welcome to this presentation on evaluation of mechanical assets with infrared. My name is Don Donofrio, and I am from the Snell Group. I'd also like to take this time to thank LRVS for providing us the opportunity to give this presentation. A little bit on my background. Went to the University of Texas, El Paso, and I joined the Navy for 20 years. When I got out of the Navy, I went to work for PDMA for almost 5 years. They make electric motor test instruments. Worked for Rockwell Automation when Reliance Electric was part of that organization. Worked for Industrial Vibration Consultants for a while, and then I've been with the Snell Group since 2001. As you can see, I was in the submarine service, and over on the right-hand side, you can see 3 submarine sails sticking up through the polar ice cap at the North Pole. This was on 6 May 1986. That image should tell you 2 things. That's the epitome of reliability, be able to operate in and around the Arctic ice cap. And number 2, that Don's getting old. On the top center image, you can see the Air Force actually flew over and dropped mail to us at the North Pole. Quite interesting. All right, mechanical equipment infrared inspections. I consider mechanical infrared the most powerful application for thermography. You have electrical inspections, you have building and roof inspections, you have the NDT, which is growing in the aerospace industry, but the most powerful to me is mechanical infrared inspection. Anything that heats up or cools down as part of its failure mechanism, if it's within our field of view, we can see it with infrared. Here's an example. This is the paint kitchen at the Ford Motor Plant, and those are pump motors up on top of those vats of different colored paints. In order to be effective at mechanical infrared, you need to understand radiometry and heat transfer and the operation of the machinery. You also need to understand the heat-related failure mechanisms. And it's not a real difficult task. It's simply we're looking for thermal patterns. And here you can see that pump assembly. There's an obvious difference between the bearing housings on that pump. It's not a super difficult process in relative comparisons in a lot of cases. So you start with a baseline on each piece of monitored equipment, and you trend from that. Some of the things we can see, and I believe me, this is a very small list. The list is considerable, and you'll probably be thinking of a bunch of things during the presentation. I'm not going to read the list, but we're going to kind of cover a lot of this. One of the most critical things, there's motor bearings. Okay, anything that spins or turns has to have something to mitigate friction, and bearings is a very common application for that. Some of the problems we can have with bearings is over lubrication. If you over lubricate a bearing, it's going to compact that grease in the bearing housing. It's going to cause excessive heat and friction. Bearing can overheat for a number of reasons, and we can see that with infrared. Lack of lubrication is a common reason. Misalignment is another common cause of bearing heating. So again, it's relative comparison. We can compare it with similar bearings on similar equipment under similar loads. If we don't have that ability, then we trend it to itself. Now, most motors, for example, they're going to run around 140 to 150 degrees in most applications, and the bearings should not be that much excessive temperature either. They normally run in the 140s or so. On normal applications, there are reasons for variance, but Now, there's going to be a difference between the drive end bearing and the opposite end bearing on motor applications, because usually on a fan cooled motor, the fan's going to be a back end, so it's going to get more convection. It's not going to be running as hot, but it doesn't have the enclosed area, so it doesn't contain the heat as well as the drive end of the motor. Now, normally that's about a 10-degree Fahrenheit, 5 degrees Celsius variance in temperature between the opposite and drive end bearing. And another thing, when you put a new motor in, or you put a motor that has been rebuilt in or rewound, it's going to have new bearings. You'll need to let that have a run-in time for about 24 to 48 hours. And the bearing temperatures are going to be about 16 degrees Celsius to about 29, 30 degrees Fahrenheit higher until the run-in period takes place. Now, on the bottom image here, you could see a motor, and that drive end bearing in that area is 148 degrees as the highest temperature. And this particular organization, they have determined that that bearing needed to be replaced. So you see the image on top, 148 degrees Fahrenheit, and then they replaced the bearing, and they let it run in for 24 hours, and notice that you see about an 11-degree Fahrenheit temperature difference. So motor bearings, trending and correlation validation with vibration, ultrasound is always a good thing to do. Very important. Pre-inspect after repairs. All right, so motors, okay, very common industrial application. Just in the United States alone, and almost 25% of all energy consumed in the United States is consumed by electric motors. Now, IR is not a primary test method, but we can find a lot of things going wrong with motors if we look at them thermally. There's other technologies, motor current analysis, motor circuit evaluation, and resistance to ground testing. If you do nothing else with your motors, I would recommend you do resistance to ground testing, because all the failure mechanism with motors cause the motor to run hotter, which thermally degrades insulation. And if you're trending the insulation, you can see degradation occurring as it happens. Now, motors are rated by the thermal limitations of the winding insulation. NEMA used to have a bunch of different insulation classes and subclasses. Now they've broken it down basically to 4 classes. A good rule of thumb for evaluating motor temperatures is the exterior is going to run about 20 degrees Celsius, about 36 degrees Fahrenheit cooler than the internal temperature. So if you use that as a thumb rule or a guideline, that should keep you in the ballpark for monitoring motor temperatures. So NEMA has reduced the classifications down to 4 basic classes: A, B, F, and H. As you progress further through the alphabet, the temperature of the insulation system can withstand higher temperatures. This chart shows internal and external temperatures with both Celsius and Fahrenheit. So here you can see an open grip-proof enclosure motor, and you can see the cooling passages there on the right are all blocked with ambient dust. And that motor, look at it, is up to 230 degrees Fahrenheit. Again, shouldn't be much more than about 140, 150 in most applications. Here is a motor that was in a potash mine. It was completely blanketed in potash, and after they got it all cleaned off, the pad eye temperature right in that area was the hottest on the motor. It's about 313, 314 degrees Fahrenheit. You can see that the fan shroud was all compacted. The fan had come off of the rear of the shaft, and they shut it down for about 5 minutes, cleaned everything off, cleaned the fan shroud, put the fan on, and initial temperature is 314, 156 degrees Celsius. And then 3 hours later, it was down to 143 degrees Fahrenheit. So it went from 313 to 143 in a little over 3 hours. Convection is very powerful and necessary for motors. So we have to get power from motors to whatever applications. One of the most common ways is through couplings, and we can tell a lot looking at couplings thermally. You need to have access to both sides, which can be quite difficult, but there's some ways to mitigate it. Here you have expanded metal, and you can see that you have pretty much balanced temperature here. Some more images. If coupling's out of alignment, heat can build up on one side or the other or both. So it's very important that you get access to both sides of the coupling. Also need to be very safe working around rotating equipment. More images of couplings. And here's the classic signatures. Look at the palette over here on the right. The red and white is up at the top. Yellow and red is in the middle. So using these rainbow palettes, you have to have a good differentiation between white and yellow. If you're off, you can misjudge it. So the image on the right, the problem is at the motor bearing. The image on the right is the coupling, and the image on the left, the problem is at the motor bearing. There's some pillow block bearings. You can see the inboard bearing on this application. Another one with the outboard bearing. Here we have a bearing that was fed from an auto greaser and said it's not working properly. The reservoir wasn't full. After they filled the reservoir and applied to the bearing, notice the temperature is significantly lower. It was up over 200 degrees Fahrenheit. Slow speed bearings, very difficult for vibration analysis. Even getting access to them can be very difficult. Ideal application for infrared. We can look at these. We can use what we call a saturation palette, where we set it at a certain temperature, and anything above that temperature will appear a certain color. In this case, red. So we know when we see that that temperature of that bearing is above our set point. So using this, it's very expedient to find bearing problems, especially on conveyors in areas where vibration is just not practical. It can also a great application for confirmation with ultrasound. Universal joints is another method of providing power or delivering power to whatever's being driven. And they have the sealed type, and they also have the lubricated type. This type has a Zerk fitting. It's lubricated. Now, these things are generally spinning so fast that we can't really get a good image of them thermally when they're in operation. So the best thing is to get in proximity, get set up, shut it down, and then take a look at it. You can see a great image of a universal joint. Now, if these come apart, they're going to potentially cause a lot of damage. One side is going to stop abruptly and hit whatever. The other side's going to continue to flop around until somebody shuts the equipment down. Constant velocity joints, used in a lot of motor vehicles, front-wheel drive, all-wheel drive, but they're used a lot in industrial applications as well. And some of these are lubricated and some are sealed. A great image of a failed CV joint. When they happen, the failures are usually rapid and catastrophic. Belts, another way of providing power to whatever we're driving. And there's not a lot of things that can go wrong with belts. Okay. And again, here we have a belt that's driving a sheave from the driven sheave, and the majority of the belt at any instant in time is going to be in the ambient air between the sheaves. So temperature should be close to pretty much ambient temperature around the motor. We recommend setting an alarm at about 60 degrees Celsius, 140 degrees Fahrenheit. And again, if we're measuring something through a guard, we're also going to be getting part of our temperature from the guard. You can also use vibration, strobe light. Also, motor current signature analysis is good for identifying belt problems. Now, when you look at these thermal images, you can glean a lot of information on what's going on if you know what to look for. Look at this image, for example. You can actually determine the direction of rotation of that motor if you look closely. Look at the top belt, the top of the belt. Look at the side of the belt. It's a lot cooler when it at the top of the sheave, and it's warmer at the bottom of the sheave, which tells me that that sheave and that motor is rotating in a clockwise direction, viewed from this side. Here's a pillow block bearing that went bad because somebody had the belt tension too tight. Do you use belt tensioners? Here we can see misalignment. And all I need to see is one sheave. Notice the outside of the sheave versus the inside of the sheave. They're different temperatures. They should be balanced temperatures. So this belt is rubbing more on this side. On the top, it's going to be just the opposite thermal pattern. So here you can see another misalignment. Look at the outside of the bottom sheave versus the outside of the top sheave. It would be, if we look from the other side, it would be just the opposite. Belt sets, it's very important that you use matched belt sets. Even in this day of age of computer accuracy, if you don't have a matched belt set, you're asking for trouble. And again, greater than 206 degrees Fahrenheit, is that that's the highest temperature in that image? Is that normal operating temperature? I doubt not. Here they replaced the belts, but they didn't use a match set. Now it's greater than 276 degrees in the hottest area in there. And here with a match set, it's less than 102 degrees, which is pretty much what you're going to see on most belt applications in ambient conditions. Refractory. This is an insulated material used in a lot of ovens and things like that. So we can see with less thickness, we're going to get greater conduction through the weaker areas of insulation. Another area where we could use a saturation palette, or what we call an isotherm, to highlight the areas that have deficient insulation. Here we have a rotary kiln, which is lined with refractory brick. And this thing spins at a very low RPM, and it's at an angle, and it's transporting things from one area to another. And what will happen is it's rotating, and whatever is in there will reach an apogee, and then it'll fall. And that happens constantly. And every now and then, whenever it falls, it'll break loose some of the refractory. And we'll get areas where we'll have differing thicknesses of the insulation, and we'll see greater conduction on the outside. So we can monitor for a critical temperature, and when that gets approached, then we know we have to go in and repair or replace that refractory insulation. Pipe insulation. A lot of pipes have insulation, and then it has a cladding. Now, if that cladding is aluminum, we're not going to see anything. Shiny metals do not give off thermal energy. They reflect the temperatures around them. Now, we could take and paint areas of it and look at it that way, but if it's clad with plastic or something like that, no problem. We're just looking for differences here. You can see there's some leakage of whatever liquid is in that pipe. The insulation's wet. The wet insulation conducts differently than the dry insulation, and we can see that we have a leak in that insulated pipe. Here we can see different tank levels. Okay, we're using the differing properties of water and air. Water has 3,500 times the thermal capacitance of air. In other words, it will hold and retain its heat much better than air does. So as soon as the sun goes down in the afternoon, giving the outer skin a little bit to change temperature, we can see the warm air at the top and the cooler liquid at the bottom. You see 3 different levels in those 3 tanks. Here, you can inspect the tank even if it's insulated, but if you have a double wall tank, they're nearly impossible. And again, if it's a shiny metal tank, stainless steel or something like that, we can't see a tank level unless we do something to increase the emissivity of the outside. In other words, make it thermally conductive. If it's a small tank, we could put a strip of tape, or we could put paint a stripe on it, but increase that emissivity.
Thank you, everyone, for attending the presentation. Don, unfortunately, is not here to answer any questions, but if you do have any questions, feel free to reach out to him directly, and I'm sure he'll get back to you as soon as he can. I encourage everyone to connect um, and discuss more about the mechanical infrared inspections presentation. It was actually very informational. Had tons of cool pictures and slides. Again, if anyone has any questions, please feel free to reach out to Don Donofrio directly. And thank you very much for joining. Take care and have a great one. Bye bye, everyone.